Hello, this is Marvin B. May, and we'll be doing a navigation exercise. The title of the exercise is Simplified Heuristic Long-Term Inertial Navigator Error Analysis. Let's say something about the words in the title. Simplified refers to the fact that we will be making many assumptions. Normally, an error analysis for inertial navigation takes more than 9 nonlinear time-variant differential equations. These are largely intractable, and one cannot find self-contained solutions to these equations. So we'll be trying to reduce these to 3 linear time invariant equations utilizing many assumptions. Heuristic refers to the fact that this is primarily for educational purposes. Long term refers to the fact that we'll be addressing navigation such that ship navigation, which we'll be talking about hours, days, as opposed to minutes and shorter. This is most applicable to ship inertial navigation. Error refers to the fact that we'll be doing an error analysis as opposed to a whole value analysis. So our objectives in this exercise are to examine long-term, that is generally considered greater than Schuler period or 84.4 minutes, propagation of latitude, longitude, and heading errors due to initial condition errors in latitude, longitude, and heading, as well as due to gyro biases. This type of exercise is not generally included in navigation books, as their level of mathematical rigor usually is considerably more difficult than we'll try to accomplish in this exercise. The fundamental assumptions we will be making are as follows. Assume a non-accelerating ship, so there are no accelerations and no accelerometer errors. Assume roll and pitch rates are 0 and there are no tilts. For simplicity, although this is not a fundamental assumption, also assume that roll and pitch are 0. Neglect any Coriolis accelerations. We'll also assume a spherical Earth of radius r, that is no eccentricity, and factors such as lever arms, sizing, and other similar type factors we will not include. So with no accelerometers and no accelerations, no tilts, and also no vertical, that is up and down channel, essentially gravity has no participation in the error analysis. This equivalently means we are also neglecting the Schuler loop. Inertial navigation is sometimes regarded as a servo mechanism which tracks both the Earth rate vector and the gravity vector. In this case, we will only be tracking from a servo standpoint the Earth rate vector. In terms of looking at gyro errors, we'll be assuming all gyro errors are biases. That is, there'll be no angular random walk or any scale factor errors, no misalignments, no non-orthogonalities. We'll also assume that small angle errors apply. That is, the errors essentially are less than 1 degree so that we can perform linear analysis and essentially make sine theta equal to theta in radians and cosine theta equals to 1. Note that despite all of the above major assumptions, this type of analysis has been useful for long-term inertial navigation analysis. So for a strap-down inertial navigator, we can say that what is sensed by the gyros, which are angular rates with respect to inertial space, equals attitude rates, that is roll, pitch, and heading rates, plus transport rates, that is horizontal velocities and vertical velocities, plus earth rates. As I said previously, we are discounting any vertical motion and any tilts and any accelerations. In this case, the attitude rates will only be heading rates, and earth rate will be 15.04 degrees per hour around the polar axis. We want to use the gyro outputs to eventually obtain latitude, longitude, and heading given initial latitude, longitude, and heading. Essentially, our task is to derive errors in latitude, longitude, and heading from gyroscope bias errors and initial condition errors in latitude, longitude, and heading. Note that the initial longitude error is just an initial condition with no subsequent effect on any propagation. Given the previous assumptions and constraints, consider this as a functional block diagram of our process. Our inputs consist of two level gyroscopes, which measure inertial rates, and one vertical gyro, also measuring inertial rates. Our additional inputs are initial conditions for latitude, longitude, and heading. With those 6 inputs, our outputs are longitude, latitude, east and north velocity, as well as heading. Remember, our constraints are that we have no accelerations and that we're going to assume roll rates and pitch rates are 0. So we could determine the velocities from the horizontal gyro outputs as here, and then we could determine heading rate by subtracting the computed transport rate and earth rate from the vertical gyro output. The integrators are shown over here. This integrator represents the heading integrator, and the integrators to obtain latitude and longitude are shown over here. We'll refer to the equations that represent this block diagram in future slides. This slide provides a derivation of the Earth's angular rate vector in geographic coordinates. We begin with the Earth angular rate vector expressed in inertial coordinates. In inertial coordinates, the Earth's angular rate vector is 0, 0, and capital Omega in the polar direction. Remember, the first 2 coordinates represent the equatorial direction or equatorial plane, and this is the polar plane, the 3rd coordinate. We could then try to express the angular rate vector of the Earth in geographic coordinates, where G is the superscript that represents geographic coordinates. In this case, it will be northeast down coordinates. So in order to get geographic coordinates, we convert the angular rate in inertial coordinates first to ECEF, and then from ECEF to geographic coordinates. We could represent the direction cosine matrix transformation that goes from ECEF to geographic by the commutative Euler rotations, longitude about the 3rd axis, and then minus pi over 2 minus latitude about the 2nd axis. And this is written out over here, multiplying the 3 the three matrices, with the last matrix actually being the column vector of omega IE expressed in inertial coordinates, 0, 0, omega, we obtain for the Earth angular rate vector expressed in geographic coordinates is omega cosine latitude in the north direction, 0 in the east direction, and minus omega sine latitude in the down direction. The 0 in the east direction is a characteristic that gyro compassing alignment utilizes. Okay, now we're going to derive what we call transport rates in geographic coordinates. We begin with the fundamental equation associated with derivatives of direction cosine matrices. In particular, we say that the derivative of the direction cosine matrix that transforms geographic to ECEF equals the direction cosine matrix times geographic with respect to geographic to ECEF times the skew symmetric matrix of the angular velocity of geographic with respect to ECF coordinate frame expressed in the geographic frame. Remember that the derivatives of direction cosine matrices have the nice property that they're represented as a vector in effect that has three components. We could then transform this by pre-multiplying by the direction cosine matrix from ECEF to geographic and obtain an expression for the skew symmetric matrix of the angular velocity of the geographic frame with respect to the ECEF frame expressed in geographic coordinates as this expression. Then rewriting the transformation from geographic to ECEF again as the commutation of two Euler rotations. We could then take the derivative of this and differentiating by parts, we obtain this expression for omega EG in the geographic frame. And then multiplying out these matrices, we obtain this skew symmetric matrix with the elements of 1, 2 as minus longitude rate times sine latitude being skew symmetric, that has to be the negative of the 2, 1 element. Similarly, the 1, 3 element is minus latitude rate, which has to be the same as the 3, 1 element, except for a sign reversal. And similarly for the 2, 3 element being minus the 3, 2 element. Note that a skew symmetric matrix has three unique components representing a vector. The 1, 2 component generally represents, or in most books represents, the third component of the vector. We can also write the transport rate, angular velocity, in terms of the translational velocities, VE and VN, as VE divided by the radius of the Earth. Again, remembering we're using a simplistic spherical Earth model. Normally this would have eccentricity terms in there and latitude terms when we take into account the oblate spheroid. However, for a pure spherical Earth model, we could represent it this way. and the third element is minus VE divided by R tangent latitude. Note that the transport rate in the down direction, which is the third element, has this tan latitude in the down component, meaning that as the platform approaches the north or south pole, the angular rate in the down component expressed in geographic coordinates starts getting infinite, which is why when we go to the poles, we often use a universal transverse Mercator or a wander-azimuth form of coordinate system to eliminate that possible singularity as we get near the pole. Here we repeat the Earth rate that we derived previously in geographic coordinates, and note that the attitude rate, which we don't show here in geographic coordinates, is just heading rate because we're assuming roll rate and pitch rate are zero, and heading rate is, of course, in the down direction. Hello, this video is to remind you of the three predominant types of angular motion that a vehicle experiences as it traverses the Earth. The first motion is simply rotation of the Earth at approximately 15.04 degrees per hour in the polar direction. That translates to omega cosine latitude in the north direction, 0 in the east direction, and minus omega sine latitude in the down direction. The other motion we experience is what's called transport rate. As the vehicle travels north, it experiences a transport rate, and as the vehicle travels east, it experiences a transport rate. The down component in the geographic coordinate frame of the transport rate, remember, is VE tan latitude divided by approximately the radius of the Earth. Of course, as we go close to the poles, that down component becomes infinite, which is why we eventually go to wander-azimuth coordinate systems or universal transverse Mercator coordinate systems. The other motion that a vehicle experiences with respect to angular rate is attitude rate. That is roll motions, pitch motions, and heading motions. For this simplified video, we're only going to be discussing heading rates, heading motion, which of course is an angular rate about the geographic down axis. So the key point is remembering that a gyroscope measures the inertial component of angular rate, and that is the vector combination of those three angular rates we referred to: Earth rate, transport rate, and attitude rate. Thank you. Let's point out in our convention, heading will be positive clockwise in the level plane from north, which is a classic, usually always behave convention. Heading error is computed inertial navigation system heading minus true heading. This convention is sometimes not used in books. Now let's take a look what the gyroscopes measure. Given the assumption of no roll and pitch rate, we might heuristically think of this problem as using the three gyro rate measurements to determine the three unknown angular rates, latitude rates and longitude rates, and heading rate. So we can express the angular rate skew symmetric matrix as measured by the gyroscopes as this skew symmetric form of the measured gyroscope outputs, and actually this would be the true gyroscope outputs without adding errors, and we'll talk about errors, of course, later in this presentation. Given the transformations from ECEF to geographic frame and from gyroscope frame, which is the S frame, to geographic, and the transformation from inertial to ECEF, we can combine those to obtain expressions for what the gyroscopes measure. So the gyroscopes measure essentially angular rate of geographic with respect to ECEF expressed in geographic frame plus the attitude rate, which in this case is only heading rate. Now, what have we forgotten about? Well, temporarily we forgot about earth rate, and earth rate is very important, as we'll see. So what we have to say is that the gyroscope again measures in its own frame, which we call the sensor frame. In this analysis, the sensor frame will be equivalent for the strap-down inertial navigator to the body frame. So we could say that the gyros measure angular rate with respect to inertial space, and that equals the sum vectorially of ECEF with respect to inertial space, geographic with respect to ECEF, and the sensor with respect to geographic. That is again the expression the gyro output equals earth rate plus transport rate plus attitude rate. And now we'll express that in geographic coordinates. So saying that the angular rate of the geographic frame with respect to the ECF expressed in geographic coordinates equals these angular rates due to attitude rate and earth rate and geographic rate, we can now express the previous equation we had of the geographic rate plus attitude rate as such and do the transformation about heading and obtain a component by component equality, which essentially gives these sets of three whole value, simultaneous, nonlinear, first order differential equations that this simplistic gyro only INS needs to mechanize. Of course, we also need initial conditions for latitude, longitude, and heading to solve these equations. And note that GX, GY are the true level gyroscope outputs, and GZ the vertical gyro output. We're always talking about the subscripts for the gyro refer to the input axis of the gyro, and the notation without any superscript on the gyros refers to true gyro outputs without errors. So repeating those equations in one, these are the fundamental whole value equations that we could represent as physical truth equations. Now, of course, we never have perfect measurements or perfect initial conditions, and therefore our indicated outputs of latitude, longitude, and heading are never totally true. So we represent the indicated outputs as H with a tilde on it, L with a tilde, and the gyroscope outputs measured with a circumflex over it. This notation sometimes is not used in books. Sometimes the tilde is used as optimal estimates. So check your notations in terms of what book you are using and sometimes these notations are not used consistently. So we can say, substituting into equation 1, that the measured gyroscope outputs are equal to the indicated outputs, and utilizing the same equations, and that gives you equations 2. Note that there's no significant error in the knowledge of Earth rate, as that will assume is known perfectly in terms of being approximately 15.04, and you could carry that out. Now there's seven digits if you use the WGS84 value for Earth rate. Notice that all quantities have units of angular rate. Again, we'll use the convention that error equals measured minus true. Similarly, for all computed quantities represented by the tilde above them, we can say that the error in those quantities, delta L, for instance, equals L tilde minus true L. Similarly, for all the other quantities that we may use. Now, substituting into equation 2 of the previous slide, directly substituting, we get these equations over here, and they can be expanded directly. Note that we're not using any differential equations at this point in terms of differentials and using products of variables. We're doing straight multiplication. Now employ small angle approximation and assume that the sine of a small quantity equals the small quantity expressed in radians, and the cosine is approximately equal to 1. And also neglect products of small angles. So with those assumptions, which are often true for a high accuracy ship's inertial navigator, we get this expression represented as sets of equations 3. I note that these expressions and this level of multiplication is not usually included in most books. Subtracting 1, which was our true whole value equation, from 3, we get the error propagation equations as given in these 3 equations, which we'll refer to as our fundamental error propagation equations. These fundamental differential linearized equations, and they are linearized about the nominal trajectory or nominal point, will be used for selected cases of errors at a nominal latitude, longitude heading, and nominal transport rates in the following slides. Since we will assume that the nominal values of the above quantities we have a system of first order linear time invariant differential equations. These 3 equations can be solved in a closed form solution, which we will subsequently do. The first case that we'll consider is a nominal trajectory that has 0 velocity with respect to the Earth, a latitude of 0, that is at the equator, a heading of 0, no gyro errors, no initial latitude or longitude errors, and we need some error, otherwise we would have no errors at all. So we're going to consider only an initial heading error of delta H sub 0. The sub 0 represents the error in heading at time equals 0. Then substituting this nominal trajectory into the fundamental error equations, we obtain delta LO0 dot equals 0, delta L dot equals minus omega delta H, and delta H dot equals omega delta L. These are the linearized fundamental error equations for our very simplified case, and specifically for the case of case 1, where we're going to solve it for an initial condition of delta H0. Remember, we also had the condition of heading equals 0, latitude equals 0, that is at the equator, and also no transport rates. So if we differentiate this third equation from the fundamental error equations, we obtain delta H double dot equals omega delta L dot, and then substituting for delta L dot from the second equation, that equals minus omega squared delta H. We then readjust that equation, or move the minus omega squared delta H to the left side, and obtain delta H dot plus omega squared times delta H equals 0. Hopefully, we recognize equation 5 as a simple harmonic equation with solution delta H equals A cosine omega t plus B sine omega t, where A and B are constants that have to be determined based on initial conditions. Since the initial conditions are as follows, we can solve for delta H and A and B specifically. A equals delta H0 and B equals 0. So we wind up with the solution that delta H, the error in heading, equals the initial value of heading, delta H0, multiplied by cosine omega t. That is a cosine function with a period approximately equal to 2 pi over omega, or approximately a diurnal period, which is slightly shorter than 24 hours because inertial rate is 15.04 degrees per hour as opposed to 15 degrees per hour. So it's approximately a period of 23 hours and 56 minutes. Also solving for latitude, we get the error in latitude for this case is minus delta H0 sine omega t. So it begins at 0 and has a sinusoidal function, again with periodicity of about 23 hours and 56 minutes. And delta LO stays at its initial value of 0, or delta LO0. Now, let's do another case. And in this case, the only error we'll consider is a Z gyro bias drift error. So this will be the same as case 1 in terms of a trajectory, but with a Z gyro bias drift error of delta GZ. And we're not going to consider superimposing, although superposition is, of course, possible when you're dealing with linear systems. We'll just consider only a delta GZ error. So substituting into the fundamental error equations, we get similar first two equations, but now we have delta H dot equals delta GZ, the gyro bias, plus omega delta L. Now, if we differentiate the second equation, we get delta L double dot equals minus omega times delta H dot, which substituting into the third equation, that equals minus omega delta GZ minus omega squared delta L. And then continuing, we get the non-homogeneous equation of delta L double dot plus omega squared delta L equals minus omega delta GZ. So hopefully we remember from elementary differential equations that the solution to this equation is equal to a homogeneous solution plus a particular solution. The particular solution being the solution in general when the derivatives are zero. So we could say that delta L equals the same homogeneous equation, A cosine omega t plus B sine omega t, minus the particular solution of minus delta GZ divided by omega. Notice that all quantities should be in radians. So now solving this for the initial conditions, we can solve for A and B, and A equals delta GZ of omega, and B equals 0. So we get a solution of delta L equals delta GZ of omega times cosine omega t, plus in effect a bias term of minus delta GZ over omega. That is the gyro bias divided by the earth rate. And for heading error, we obtain delta GZ divided by omega times the sine of omega t. So both are sinusoidal, but latitude has a bias of delta GZ over omega. So these equations are repeated here for uh, purposes of repeating it. And the thing we wanted to point out is that even though we have a Z gyro bias, that is an azimuth gyro bias, our heading error is still a sinusoid and does not ramp up, at least in long term, for the assumption of a pure bias error in the gyroscope. This sometimes puzzles people, but it is a consequence that the bias offset and latitude error essentially causes an earth rate computational error in the vertical that negates the growth in heading error due to the Z gyro bias. As I said, this explains to some people's puzzlement on why for a long-term navigator and for the case of a perfect gyro bias or pure gyro bias, the heading error does not ramp. Okay, so now let's consider another case, and this case will be similar to the previous case, except we'll consider a level gyro bias error. In this case, we'll consider an error in the Y gyro bias or the east gyro. And again, substituting into the fundamental error equations, we get these. And although we explicitly went through all the equations in detail previously, it's very similar to the previous case. And we get solutions that are shown here. In this case, the heading error has a bias equal to minus the gyro bias divided by the angular rate of the Earth. Note that all quantities, again, are in radians. Case 4 will be just to exemplify the fact that things aren't too different if we remove the assumption, at least for the homogeneous part of the solution, if we remove the assumption of equatorial latitude and went to a non-zero latitude. So again, these are the fundamental error equations. Now where theta represents the latitude, just for notational convenience, I used theta not to confuse it with L. And we could go ahead and solve these three equations somewhat similar to our process, but now involving some trigonometric identities from your analytic geometry course. And utilizing those trigonometric identities, we'll obtain a similar non-homogeneous part of the solution as follows. Now, one can put in initial condition errors or put in gyroscope errors and solve specifically for the particular solution that may come out and solve for the particular case that you're examining. We'll do a case 5, and in this case 5 we'll also have a non-zero latitude, and we'll also have a z-gyro bias. So in effect, this is a case that I had previously talked about, and we can go through again these fundamental error equations, substituting into these three equations these conditions, where now we have a delta GZ, and doing similar steps in a similar process, and now perhaps adding a initial condition in latitude error, we'll get a solution that looks like such. Again, because we have an initial condition in latitude, we have a delta L0 plus delta GZ of omega times cosine latitude times cosine of omega t, which is again a sinusoid, of course, at diurnal periodicity. And we have this bias term due to the z-gyro bias, and now it's multiplied by the cosine of the latitude of this trajectory. There's a continuation of case 5 to solve for longitude error. The first equation is one of our fundamental error equations. Taking that fundamental error equation and now solving for delta LO dot, we get delta LO dot equals omega tan latitude times this expression in brackets, which was the error in latitude from the previous slide. Integrating the above equation, we get delta LO equals this expression, which is now sine omega t, and the omega disappeared in the integration process. We also had a constant for delta L, which now gets multiplied by t in the integration process. The c is an integration constant, which for delta L longitude at t equals 0 would equal 0. The viewer is encouraged to try other cases, such as those cases with transport rates and those cases with heading not equal to 0. Okay, so if we superimpose all error sources, and again, we're going to assume negligible transport rates, although you can put in transport rates into your solutions. and this is the case for zero heading, and again, we're doing this for a strap-down inertial navigator. We get latitude is some bias term, and a combination of sine and cosine of the diurnal frequency sinusoids. That is similar to heading. And in the case of longitude, we also have the case of obtaining a ramp that depends upon your X gyro bias and Z gyro bias. Now note it is a combination of the X gyro bias and Z gyro bias that depends upon latitude. And this combination is essentially a resolution about latitude into the polar frame. That is, this combination of the X gyro bias plus Z gyro bias, essentially the resultant of that is a residual effective polar gyro bias. So it's the residual effective polar gyro bias expressed in this term D that causes this ramp in longitude error. And for long-term inertial navigation, such as we said for ships or submarines, often this longitude ramp, which of course is unbounded, is often the largest contributor to long-term position error. So reducing in any way we might the effective residual polar gyro bias is a good procedure if we're interested in long-term position performance of a ship's inertial navigation. In the previous simplified heuristic derivation of long-term inertial errors, we had many assumptions. Amongst them were no accelerations, no Coriolis effects, and only initial condition errors and initial gyro biases. So let's take a look at a software program that does some simulations that represent the cases that we just did, cases 1 through 5. And I should point out that normally when it comes to inertial navigation analysis, we don't do things by hand solving differential equations. We were only able to do that for the very simple cases that we described. Although, as I pointed out, those simple cases for long-term inertial navigation are quite useful and practical and instructive. So here I run a relatively simple program that goes over those cases. In this simple program, however, we do include Shula errors. That is, we do include errors due to gravity as it acts on tilts, and we do include Coriolis. So let's take a look at some of the results of this program as they emulate the simple cases that we did analytically. Here's case 1, which has a small initial heading error. The heading error in this case is 0.94538 degrees. I'm not sure why we chose 0.94538 degrees. I believe that's something like pi over 190. But in any case, we chose an initial azimuth error, and that was the only error we're simulating, as you might remember for case 1, and also for an initial latitude at the equator, or 0 degrees. I also want to point out that 0.9 degrees or so is definitely not a small error for a high quality inertial navigator. Usually we talk about errors of several arc minutes for high quality inertial navigators. However, we could still live with the small error angle assumption of sine theta equals theta, cosine theta is approximately equal 1 when we have angles less than 1 degree. So this graph shows you the errors in azimuth for the initial condition of 0.94538 degrees in azimuth, and that's the only error, and we're at the equator. So notice it is a pure cosine function as we derived with period of approximately 24 hours or 23 hours and 56 minutes, the sidereal rate. This next set of graphs is the same case, that is small initial heading errors of 0.94538 degrees and no other errors. And you can see for this case at the equator, longitude has no errors, neither does east velocity, of course, and neither does the misalignment about north. Here is the same case, and we're taking a look at latitude error. And we see latitude error has the predominant minus sine omega t, where omega corresponds to 2 pi over t, where t is approximately 23 hours and 56 minutes. However, notice we do see these perturbations that represent Euler oscillations that get coupled in due to the coupling of gravity and tilts. These Euler oscillations, you remember, were not accounted for in our very simple analytical derivations. And here you see the north velocity error, which is in this case somewhat dominated by Euler type errors. You could also see the, say, smaller diurnal errors along this curve, and these are the misalignments about the east axis. Case 2, as you remember, has a gyro bias driving the azimuth axis, and the initial azimuth errors and other initial condition errors are 0. So what we see is a sinusoid in azimuth starting at 0 as the initial conditions insist upon, and you have a sinusoid, again, of course, of periodicity 2 pi over t, where t is approximately 23 hours and 56 minutes. And you could check our results for case 2 with the azimuth amplitude here. Check the analytical results that we gave in previous slides and see whether they correspond to the 0.001 degrees per hour driving azimuth as we derived in case 2. Here again, we're at the equator. The longitude error is 0, as well as, of course, east velocity and the misalignment about north for this case 2 case. And to complete case 2, we show a latitude error, which has this sinusoidal form. It actually has a bias in effect, a mean value that we talked about when we derived the analytical expressions. And here is the corresponding north velocity error. And again, we see some Euler oscillations and the corresponding misalignment errors about the east axis. Now we go to case 3, where we still remain at a latitude of 0 degrees or equatorial latitude. And these are, of course, all nominal. Remember, everything is a linear expansion about a nominal point. So here we did a gyro bias drift error about the east axis, driving tilt about the east axis. And again, we're using a gyro bias error of 0.001 degrees per hour, which is a medium to high quality gyro in general. Remember, we talked about 0.01 degrees per hour residual bias as, in effect, a rough number for a navigation grade. When we get sometimes better than that, we're going to towards strategic grade, but not quite strategic grade. So in this case, which was case 3, as you remember, we have a gyro bias drift, driving tilt about east, no other errors in terms of initial conditions or other gyros, and again an equatorial latitude. And we see the azimuth error has to start off with 0 as dictated by the initial condition, and then gets driven negative, again with a negative bias in this case. So try to compare these results from a numerical computer simulation with the simplified analytical results that we achieved. And remember, our simplified analytical results, we managed, because of all the assumptions, to derive simplified second-order differential equations. This, again, at an initial latitude of 0, longitude error is 0, east velocity error is 0, and misalignment about north is 0. This completes case 3, which, again, as you remember, is a gyro bias drift driving tilt about east. And we could see the latitude error, again with some Schuler oscillations, but the major long-term effect is the diurnal effect, the corresponding north velocity error, which is driven by or dominated by Schulers. In general, one could say for Schuler type effects, if one represents the velocity in knots, the position error would be about 1/5 in nautical miles of the velocity error of the Schuler component represented in knots. And this is the misalignment about east. Now we go to case 4, and now we move away from the equator to an initial latitude of 30 degrees. Again, we kept that initial sort of strange azimuth error of 0.94538 degrees, which, as we said, is a large error for a quality inertial navigator. However, it's still within reasonableness bounds for making the small angle assumption. And this is the azimuth error, starting, of course, at the proper initial condition and having a cosine type effect, and now including some Schulers. I'll also point out that as far as Schuler oscillations, most of the time we operate for long-term inertial navigation, and that generally means more than a few hours. We operate in a damped configuration, meaning that we utilize an external velocity aid, such as an electromagnetic log or Doppler velocity log to aid the inertial navigator, which helps the inertial navigator minimize Schuler oscillations and keep them bounded. Here you can see the Schuler oscillations are growing, and this is because we do not actually, in this simple program, we do not actually implement speed damping to bound the growth of the Schuler type errors. Again, continuing with case 4, we have this heading error and latitude of 30 degrees, and you could see the diurnal oscillation and of course the growing Schulers. They're quite evident here, and they are growing very large for this fairly large case of initial heading errors. As I say, you wouldn't normally have such large heading errors, nor would you normally have unbounded Schuler oscillations, because one would implement velocity damping or velocity aiding to help contain or bound these Schuler oscillations in normal operation. Continuing with case 4, we're at latitude 30 degrees again, and this is the latitude error, and these are the corresponding north velocity errors and misalignment error. One should always see a derivative and integral relationship between north velocity error and latitude error. That is, north velocity error should be the derivative of latitude error. In the previous slides, we used a simulation program to prove out the analytical results that we did earlier in the simplified heuristic inertial navigation error analysis. The simplified program is in MATLAB and had many of the same simplifications that were used in our differential equations. The difference is this simplified program does include Schuler loop and does include Coriolis. It still does not have horizontal accelerations or a up, down, or vertical loop. So we'll take a look at this simplified program. We won't go over it in any detail, which we may do in a future lesson. However, the simplified program is in MATLAB and may be straightforward for many of you to analyze, and we will be providing software that will be close to this simplified program. So this is the first slide of the MATLAB program. It's divided into 3 columns. We go from the first column, then to the second column, and then to the third column, and then to the next page. We do not show the plotting routines or printing that the program does have. So taking a look at this program, we could show that we first initialize latitude and north velocity and east velocity. Remember, we're trying to provide a nominal trajectory about which we perform our linearization. So after inputting our latitude and velocities and changing to the appropriate units, we choose which parameter or case we want to simulate. Now, if you remember in the heuristic simplified error presentation, we showed 5 cases. And the last case was a superposition of 2 cases. In particular, the last case, case 5 that is, had an initial latitude error as well as a Z gyro bias error. That requires the superposition of two errors. This simple program only treats one error at a time, so it does not treat the case of multiple errors. The case of multiple errors, since superposition is true, can be incorporated into this program. However, it is not in the program being shown here. So we choose what condition we want to simulate. We could simulate, as you remember, say an initial latitude error, an initial longitude error. By the way, initial longitude error doesn't propagate into other states. We could have a north velocity error, initial east velocity error, level misalignment about north, a misalignment about east, a misalignment about the vertical, also referred to an azimuth error misalignment. And if you remember, that was case one, an initial azimuth error. And then we could introduce three different gyro biases. Case 8 is a gyro bias about north, and 9 is a gyro bias about east, and 10 is a gyro bias about the vertical. Remember, again, case 5 in particular was the combination of a latitude initial error and a Z gyro bias error. So this is just MATLAB code for choosing which case based on the input that the operator puts in. He could choose to input either any of these 10 cases and the magnitude of those errors. So that's pretty much the first page of the program. And then in the second page of the program, shown here, we run the program, as you could see from the simulations in the previous few slides. We run the program for 2 days, iterating at 1 second at a time. The 2 days is represented by 86,400 seconds in a day times 2. Again, we neglect horizontal accelerations, and we neglect the vertical or up-down loop. The only errors we're considering are initial condition errors in latitude, longitude, or the velocities, or the misalignments about northeast and azimuth, and gyro biases. Therefore, we set up our program to have these 10 states, which represent those initial conditions, and the 3 gyro biases, which are sometimes treated as forcing functions, or they can be treated as states, as we do in this program. Now, the F matrix is the so-called dynamics matrix, and that represents the first-order differential equation relationships. In this program, as a simplification, and is often used in most high-accuracy inertial navigation analysis, we represent error propagation by a series of first-order differential equations. In this case, they're linear constant differential equations, so we could even make some further simplifications in its solution. So we're not going to go over each of the elements of the dynamics matrix F, but we could take a look at a few of them. For instance, F13 equals 1 over radius of the Earth. And that says that the derivative of the error in latitude equals the error in north velocity divided by the radius of the Earth. So state 1 is the latitude error, and state 3 is the north velocity error. And this says that delta L dot, or the error in latitude, equals the error in the rate of change of the error in latitude equals the error in north velocity error divided by the radius of the Earth. We could take a look at some of the other terms. Remember in the solution that we did for the simplified second order differential equations, G, which represents the Euler loop, and omega Euler is the square root of G over radius of the Earth, we neglected the Euler loop. So in the analytical differential equations that we solve for simplicity, we neglected the Euler loop. In this program, we do include those terms that represent the coupling of gravity force with misalignments about the level axes, and that is the Euler loop. So some of these terms, for instance, the terms that include G and include G in particular, like F45 and F36, represents the Euler loop type terms. The other terms are similar to those that we could see in the block diagram of the fifth slide in the simplified heuristic inertial error presentation. For instance, the derivative of the longitude error is equal to the east velocity error divided by cosine of latitude. Other terms that we could see, for example, in the block diagram shown in slide 5, is the rate of change of level tilt is equal to velocity east times tan latitude divided by the radius of the Earth. And if you take a careful look at slide 5, you could hopefully register these terms of the F matrix with the block diagram figure of slide 5. And that's why this program, in a sense, represents the simple differential equations that we solve for and the block diagram that we showed on slide 5, with the exception that here we include the Euler loop and Coriolis terms. So once we have the F matrix, or the dynamics matrix, we determine, for this case, a simplified transition matrix, which is determined as the identity matrix plus F delta T plus, if you want to take it out to more terms, F delta T squared over 2 plus F cubed over delta T cubed over 3 factorial. It's a Taylor series expansion for e to the F delta T. That is the transition matrix for differential equations with constant coefficients. So once we have the transition matrix phi, we essentially just have to propagate the states from a general state K to a or general state k minus 1 to a state k with the transition matrix, and keep repeating that for the duration of the 2-day simulation. So that pretty much is a description of the MATLAB simulation program, with the exception that we don't show the plotting routines. But effectively, this is the basic step that is done to generate the states from the initial condition to the final condition. So the other point that I wanted to make is that we do show Shula loops, but we don't show damping of the Shula loop, as I mentioned, and that would be another aspect of a more realistic simulation that's often done. So that is the conclusion of our simplified heuristic long-term inertial navigation error analysis. To a large extent, it's meant as a thought experiment and as an educational tool for more complex and higher fidelity analysis. Thank you.